Thanks. I'll begin with a word of prayer. So, dear Heavenly Father, we thank you again for this opportunity we have just to meet together and to study your creation. I thank you for these students. Pray you'd help them as they study for this course and others, that they'd just finish this semester well, Lord, for your glory. In your name I pray, Lord Jesus. Amen. So, guys, you have questions? Yes. 10.6, you say? Yeah, see that backpack I was talking about? I had my book in it. Yeah, that would help. Thank you. Otherwise, you'll have to wait for 5 minutes for me to go to my office and get it and come back. So 10.6? Number what? All right. Get the problem up here. Number 12. We've got R equals to 5 over 4 minus the cosine of theta. And we're interested in when theta is pi over 6, what do we want to do? What's the question ask us? We want to find an equation in x and y for the line tangent to the polar curve at the indicated value of theta. So basically find the Cartesian equation for the tangent line. All right. So the way I would, do you want me to start from just work from the start, or you have a specific question about it, or how to do it? Or?
Solve this, but my answer is incorrect. When I compare it to your
Ah. Well, there is, of course, the possibility that that solution manual has an error in it. I mean, it's not my solution manual, so I can blame them, right? But how I would do this, let's see here. What I would do is I would find the parameterization of the path, right? So like R, basically use T as theta. So R of T is what? It's, R cosine T, R sine T, right? I mean, this is my X, this is my Y. To be more explicit, X equals to 5 cosine of T divided by 4 minus cosine T, and Y is equal to R, which is 5, over 4 minus cosine T. Why is it so hot everywhere? I'm dying today. Temperature in this building. So that's X and Y as a function of time. Now you could put T equals to theta, that's fine, right? I mean, we could put theta instead of T, That's also cool. Basically, I'm just using theta as the parameter, so, you got pick your poison. That's the natural parameterization of the curve, do you agree? I mean, if you're given the curve in polar coordinates, the simplest thing to do is just to shove the formula for R into the polar coordinate transformations. That gives us the parameterization as a function of theta. And then how do you find the slope? Remember, we have this result, dy dx is equal to like dy d theta divided by dx d theta, right? So I think I'm going to back it up here for a second and calculate the dx d theta and dy d theta separately and then go to that formula rather than try and do everything at once. So what's dx d theta? Dx d theta, quotient rule, right? So I've got minus 5 sine theta times 4 minus cosine theta minus 5 cosine theta times sine theta divided by 4 minus cosine theta squared. And for dy d theta, I calculate 5 cosine theta times 4 minus cosine theta minus 5 sine theta times sine theta divided by 4 minus cosine theta squared. Now I need to evaluate these at pi over what? Pi over 6, right? So now evaluate dx d theta and dy d theta at theta equals to pi over 6. See what we get. So we got sine of, let's see here. Things we should remember, sine pi over 6 is what? 1/2, right? What's the cosine of pi over 6? Square root of 3 over 2, right? So you can plug those in here like that. We got, I don't know, is there any way I can simplify this before I just go off and start calculating like a madman? Let's see here. Anything cancel out in here? Looks like I've got a plus 5 sine cosine and a minus 5 sine cosine, right? So this cleans up a little bit. I think that's worth the algebra step. This is actually minus 20 sine theta divided by 4 minus cosine theta squared. Agree? Do you agree with my cancellation? I've got minus 5 times minus cosine gives me 5 sine cosine. And over here I've got minus 5 cosine sine. Those cancel. And hopefully we get the same cancellation down here. Oh, no, we don't. We get what? Huh. We get like a... Oh, but that gives us minus 5 cosine squared, minus 5 sine squared. There's the cosine squared plus sine squared down here, so we can simplify our life a lot if we rewrite this as minus 5 plus 20 cosine theta. Right? A little bit of algebra. Well worth it, because the evaluation here is a pain. Okay, so dx d theta then is going to be what? Minus 20 divided by 2. And then 4 minus the square root of 3 over 2, quantity squared. And dy d theta is minus 5 plus 20 times the square root of 3 over 2 divided by the same number. This is pretty awesome because I don't actually need to simplify the thing in the denominator, because after all what we're about to do is calculate dy dx as dy d theta, right? Divided by dx d theta at, pi over 6, right? And if you look at that, you see what happens is when I form this quotient, the denominators just cancel. So who cares what that number is? They cancel out, right? And you just get dy d theta, which is like minus 5 plus 10 root 3 divided by, looks like minus 10. So I get 1/2, looks to me like 1/2 minus root 3 as my slope. Was that what you got? Or you put numbers into this thing so it was big and ugly and it's hard to see if it was right or wrong, right? Yeah. And then I'm looking for the equation, right? So what do I need then? If that's the slope of the tangent line, what do I need also? I need a point, right? What's the point of, where are we when we put in pi over 6? What we got? What's r equal to? 5 over what? So this, right? So I guess I could say r is equal to, it's 10, right? Over 8 minus root 3. So that means that x is equal to 10 over 8 minus root 3 times the cosine of the angle. What's the cosine of the angle? Square root 3 over 2. What's y equal to? 10 over 8 minus root 3 times the sine, which is a half, right? So apparently, I mean, it's not terribly enlightening, but the point on the line is, I don't know. I mean, I'll leave it just ugly. So 5 square root of 3 divided by 8 minus root 3. You could rationalize that if you wanted to. I don't. And then this other one is 5 over 8 minus root 3. Let's see here. To get some sense of where that is, 8 is 8. Root 3 is like, it's almost 2. So that's about 6 in the denominator. 5 over 6, it's a little bit less than 1. So this is kind of sort of about like where 2 comma 1 is, give or take. Point is somewhere there, and the slope is this thing. This is, again, 1.7 something, so this is like a slope of minus 1.2. So the tangent line looks something like this. I guess it didn't ask us to graph it, did it? Sorry. So y is equal to, what do we got? 5 over 8 minus root 3 plus the slope, which we figured out is 1/2 minus the square root of 3. That's the slope. And then x minus 5 root 3 over 8 minus root 3. This is using point slope formula for a line. There you go. That probably doesn't look like the book's answer, and I don't much care. I mean, it's the concept that's more important than the actual rationalizing roots in the final answer or something. Does the book have a decimal answer, or does it have some kind of radical answer? No. Yeah, this problem's pretty tough, right? I mean, it's got some nice calculation in it. Most of the difficulties, calculus 1 or pre-calculus though, right? I mean, the calculus 2 content here basically is just realizing that for, well, 2 things, I guess. One is that to find the slope of a parameterized line, we take the slope of we take the quotient of the rate of change for y and the rate of change for the x parameter, right? And also to form a parameterization for a polar curve, we can use the polar equation plugged into the usual polar coordinate formulas, right? So like this is a standard technique. Here, let me work a simpler example. If we have r equals to theta, find tangent line at theta equals to pi over 4, right? So my parameterization here, x is equal to theta cosine theta, y is equal to theta sine theta. So dx d theta and dy d theta are what? We got ourselves a cosine theta minus theta sine theta. And here we got ourselves a sine theta plus theta cosine theta. So therefore x prime of pi over 4 is, square root of 2 over 2 minus pi over 4 square root 2 over 2. And y prime of pi over 4 is what? It's root 2 over 2 plus pi over 4 root 2 over 2. Which you could probably write prettier, right? This is really square root of 2 times a half minus pi over 8. I mean, I could have pulled out the 2 too. But I don't know, I just like to leave the square root 2 out front like that. I don't know, it's probably not defensible. Probably I should pull out the 2 as well. All right, it's bothering me. I'm going to pull out the 2. Square root 2 over 2. Square root 2 over 2. 1 minus pi over 4. 1 plus pi over 4. Okay, enough of that. So then there's the rate of change for x, the rate of change for y. The slope of the parameterized curve is given by the quotient of those. We work that out. geometrically, and you can also work it out by the chain rule. But anyway, so what's my slope? dy dx equal to, dy, well, y prime of pi over 4 over x prime of pi over 4. And this is dy dx at which point? At the point theta equals pi over 4, right? Now we could be more specific about what that is, but we got what? We got 1 plus pi over 4 over 1 minus pi over 4. As you can see, I've reaped the benefit of factoring out a common factor in both, right? Because they cancel. I did the same algebra trick in both of these problems, right? Which is to recognize I've got some kind of common nastiness to both. So when I form the quotient, I don't even need to write those down because I know they cancel, because I can think rather than write that. Now, I guess I can clean this up a little bit. I'll multiply by 4. That's 4 plus pi divided by 4 minus pi. So I kind of like that more as an answer for the slope. Now what's the Cartesian equation? What do I need to find? What's the point of tangency? X equals to pi over 4 times the cosine of pi over 4, right? Also known as the square root of sorry, brain fading. Pi root 2 over 8. And what's y? Same thing, right? So the equation for the tangent line is y is equal to pi square root of 2 over 8. Slope, my slope was 4 plus pi over 4 minus pi. And then x minus pi root 2 over 8, yeah. So there's another of the same kind of example. But I think with an easier polar curve than the one we were given, right? So. What does this curve look like, by the way? R equals to theta. It starts out at 0, right? When theta is equal to pi over 2, it's here. Theta equals to pi, it's over here. 3 pi, it's down here. So it's this deal, right? It's a spiral. And I think we just, well, my picture's not quite right, but let's see here. At pi over 4, this is pi over 4, right? Let's see here. It's pi, let's see, how big, what is this? This is like square root of 6. I don't know. I don't have a good sense of numerically what that is. Anyway, it's I don't think I quite got that right yet. What's that? My picture isn't quite right. It's got a positive slope, right? Yeah. So however I'm doing this is not quite right. I mean, somehow when you hit that point, you've got, at pi over 4, you got some kind of, the tangent line is roughly speaking this thing. I'm not doing a very good job of picturing it, but I should use another color really. All right, I'm going to shut up. Do you guys have other questions? Mm-hmm. Mm-hmm.
Question 15.
10.8, number 15? Okay. I will try. Oh, you're fine. Let's see here. Oh, yeah, there was a there. All right. surface area, huh? Is that right? So here we have, we're supposed to find the surface area of y equals to cosine x, 0 less than or equal to x less than or equal to, I didn't do this one? I have a sudden feeling like I did this, but I don't think I'm right. This one, right? Oh, it was, okay, that's what it was. Thank you. So this, we're supposed to find the surface area of this thing, is that right?
Yep.
Okay. So, revolve this curve around x-axis, find resulting surface area. So, roughly speaking, cosine looks like basically this from 0 to pi over 2, right? It goes from 1 to 0 on that thing. And so we're just basically taking that and revolving it around the x-axis. Right? Like this. And trying to find the surface area of this shape. Right? Now, we worked that out. We said that the surface area should be equal to the integral from 0 to pi over 2 of 2 pi y, the square root of dx dt squared plus dy dt squared. It looks like I'm going back to what we did yesterday, but to be more honest here, I'm setting x equals to t, and I'm setting y equals to cosine t. So I'm suggesting that this right here is my parameterization, right? I can just use x as the parameter in this case, so that's how the formula we looked at works for this case. Of course, what that means is that dx dt is just 1. And so the book probably has a standalone formula for this. I forgot to look, but 2 pi cosine t square root of 1. What's dy dt? It's minus sine t, right? But you square that and the minus goes away. So we just have 1 plus sine squared t. And then dt. I love the integration in this section. It's so much fun. This is a u substitution. Just let the inside of the radical be u. I think that'll do it. Let's try that. So if we let u equal to 1 plus sine squared t, right? That makes du 2. Ooh, that's not going to do it. Es no bueno. No. That's give me sine cosine. I don't have a sine cosine to play with.
Their solution, they did a u substitution with sine.
Okay, let me try that. So that gives me cosine t dt. That was my next thing. But let's see here. So that, then you got to change the bounds too, right? U of 0 is 1 plus 0, which is 1. U of pi over 2 is 1 plus 1, which is 2. So I got to change the bounds, change the measure. So integration from 1 to 2. What is it? Oh, yeah, you're right. I'm sorry. I'm sorry. I'm getting ahead of myself here. So just 0 and 1, right? Well, that's better. I much prefer this integration, right? So now what was your question about this question, though? It seems like you maybe already know.
Well, I kind of got confused after that part.
Oh, okay. So we're almost to the part you need help with then. So this is, so we're good up to now? Does that make sense so far? I mean, all right. Now, how do you integrate the square root of 1 plus something squared? Indeed, this is nothing to sneeze at. Oh, was it a hiccup? It's also nothing to hiccup at. I'll take whatever I can get. Let's see here. No, this is an unfun integral. I mean, well, depends on your viewpoint. I guess if you don't know how to do it on a test, it's unfun. If you do know how to do it and you're a bad person, you're like, haha, I know how to do this. The other people don't. Hopefully you're not that person. Let's see here. I think the way I would do this would be to make a u equal to sinh phi substitution, because I know that 1 plus sinh squared phi is equal to cos squared phi, right? So that will give me integration, and let's see here, sinh of, in order to get u equal to 0, I need phi 0. This would be inverse hyperbolic sinh of 1, that bound, and I got myself a 2 pi, I got myself a square root of cos squared phi, and then over here, I've got cos phi d phi from the differential. So that gives me integration from 0 to sinh inverse of 1, 2 pi cos squared phi, d phi. Now, did the book do integration by parts on a secant cubed or something?
It didn't really explain it.
Oh, it just right there.
It just like skipped those steps.
Oh, it just said this integral's this?
Yeah.
Yeah, that's not nice. This is a hard integration. But it's one we've done before. But this is a integration that a lot of you missed on test 1, yes? So, perfect question for the final, really. Let's see here. Integration from 0 to, hey, I told you about it, though. So that probably means it's not on there, right? And you're like, wait a minute. You should really watch The Princess Bride. It explains much. Let's see here. 2 pi times 1 minus plus the cosh of 2 phi. Well, fine. And you guys are giving me a workout today. Let's see here. That is equal to what? We're almost there. So this is pi times sinh inverse of 1 plus 1/2 the cosh of 2 times the sinh inverse of 1, and then minus the thing at 0, which gives me 0, and then minus, put phi equals 0 into this, gives me a 1. And of course, you can find a numerical value with Wolfram alpha or something. If this was a question on the test, I would be like, that's answer. You don't have to find the decimal, obviously. I mean, if I know what's good for me, I'll just say set up the integral that calculates the surface area of this, but do not calculate, right? If I say that, what is it? Whoop. If I say set it up but do not calculate, then you can stop basically right here, right? Set up but don't calculate would make the answer this thing right here. If I say, but do not calculate, and then you try to calculate, only to find out that it's really awful, does that impress me? It does not. It saddens me. For all the other points you lost at other parts of the test by wasting your time on this part. Yes. Oh, no. Oh, yes. Thank you. Yes, the integral of cosh is sinh. Very good. Thank you. Knew something felt wrong here. Any other corrections? I was about to say, Mr. Kang, they beat you to it, and now I understand why I'm not saying that. Okay. It's nice to have him not around. I mean, it gives the rest of you guys a chance to correct my errors. It's good. That can be simplified with hyperbolic identities and stuff, but I'm resisting the urge to do that because that's not what we're doing at the moment. So, did you have another question, you guys? One of the problems we haven't worked yet that we should is the problem of intersection versus collision. Those are interesting. We should look at those. Give me a second here to look up one. So the distinction between there's a lot of variance on this. Like the question I like to ask sometimes is like about ninjas. So the question goes something like this. Here's basically the question. You have ninja, let's say Bob. All right, this guy's a genin. In other words, he's a low level. Pretty unskilled, not much skill. He really doesn't know much in the way of ninja arts. And so you imagine Ninja Bob is going along some path, right? Like this. And so we could say R of Bob of T is, that's where Bob is, Ninja Bob at time T. And then you can imagine another ninja, right? Let's say ninja, I need a name. What do you want to call him? It could be a her. I mean, it's Trump's America. It's all women. I mean, look at the cabinet, right? It's a brave new world. See here. Who'd have thunk it? I very much enjoyed watching one of these mainstream media people going, he's nominating women to the cabinet. They're like genuinely confused. It's like, but he's against women. Why is he doing this? It's confusing to us. It's funny to me. But anyway, where was I? Sorry, I know most of you guys are Jill Stein supporters. I still sore. I think my cousins voted for Jill Stein. Adds to my belief that my uncle's not that smart. See here. Raise children to do such a thing. My little sister probably would have too. I think my little sister felt the burn. So I think she couldn't bother to vote in the end, which was just fine with me. So that's right, Mary. You should relax. There's no need to vote this year. Just take a day. My little sister has a master's in English from the grounds of the University of Virginia. So, they don't have a campus, they have the grounds, if you've ever been up there. It's really something. And that, I'm trying to find something if you haven't figured that out. I really should just focus on finding it because I don't multitask well, obviously. But, too many files on my computer. Come on. Why am I looking up Calculus 3? What's wrong with me? Like, which class are we in right now? What are we doing? Calculus 2? Yes. Anyway, I went to her graduation ceremony. I've never heard such unadulterated nonsense as that graduation ceremony of a master's in English at a UVA. It was amazing. the change in the world starts with the thesis projects of master's students in English at the University of Virginia. I was like, asked my sister afterwards, I'm like, do you guys really believe anything they said up there? And she's like, no, we just say it to make ourselves feel better because we can't get jobs. So it's like, okay, Mary. I'm glad that you have not had all of your common sense removed by this thing called English. Let's see here. I was looking for something. I know I was. Where are we? There it is. Oh, come on. Oh, we didn't come up with the name for the second ninja yet. You guys gotta give me a name. Carl? Very good. I like that. Come on, I can't find this stupid problem. At least we got a name. Name names. Okay, so Carl. And Carl is an elite ninja. If you're into Naruto, he'd be at Jonin level. And then so you imagine Carl and like this, right? Here's Carl's path. So here's a typical position of Carl at time t. And then the deal is Carl is an elite ninja, so that means that if he crosses the path of Bob, right? And you have to imagine that this is in some sort of thick forest, so it's not like an open plain where they could see each other. They're going through some thick forest or something. But the thing is, one of Carl's ninja skills is scent. So if he crosses the path of this low-level ninja who has not learned the art of hiding one's scent in travel yet, well, if he crosses the path of Bob at a time later than Bob passes that point, well, then he's in trouble because then Carl's going to stop going where he was, and he's going to follow Bob and kill him because, of course, every ninja wants to kill every other ninja because it's what they do. So, like, the question then is, the survival of Bob basically is based on the question, find intersections of these two paths and judge their relation in time. Like, which one comes first, which one comes second. If Bob crosses the path of Carl after he's been there, since Carl is not well-versed in the temporal arts of, he can't do any kind of time travel and notice that things happen to his future. Past. Future, yes. So basically you're looking for these points of intersection. Points of intersection, like these, you get from just solving what? You get from solving that our Bob at time t is equal to our Carl at time t, like that. If you find a solution to that, that's not right. What would that give you? You don't need ninjas to think about that. You can think about what are those, where they get the old cars and they take a big field or something and just drive them at each other in some sort of crazy 8 pattern. Like what's it called? Not monster truck. It's more interesting than that. Yeah. Demolition derby. So what you're talking about there is just a collision, right? At the same time is not intersection of paths. That's just a collision, right? So if I want to find intersection points, I have to use different parameters, right? But that would give me points of intersection, and then I can see, who got there first. Now, in order to make this problem interesting, of course, I need some formulas, which is what I'm having trouble finding. I just found this the other day too, and I can't remember where I put this example. I guess I could just search why don't I just be a sensible human being and search intersection. Oh, there's a lot of intersections. Maybe collision. I can't say a collision that much in these notes, right? No matches were found. I probably misspelled it. I'm not good at coming up with the formulas on the fly. Do you guys happen to know one in the book that I'm forgetting about? Oh, I know where I found it. I saw it when I was looking at your problems the other day. Now, I've added the ninja bit to it, but it's the same question. I think Dr. Smith had one based on the Millennium Falcon. I was very proud of him. He was showing me. I was like, wow, it's very nice. The algebra of these problems is surprising and different. It's probably not algebra you've quite done before. It's interesting. I will eventually find these. Well, maybe I won't. I can never. I thought it was under the parametric curve section here. Oh, self-intersection. Well, that's self-intersection. That's what I want. Oh, there it is. So you have two particles, ninjas. One is x equals to 2t plus 6. The other one is y equals to, I mean, the same, these are the x and y parameters for the one thing. I'm writing these collectively, and the picture over there is r of t equals to, 2t plus 6, comma, 5 minus 4t. So maybe that's, let's say that's Bob. And the other one, this is number 43 on page 502, is x equals to 3 minus 5 cosine pi t, and y equals to 1 plus 5 sine pi t. All right. We're asked two questions in this problem. At what points, if any, do these paths intersect? At what point, if any, do these particles collide? Now, there's a variety of different ways to go about solving these problems, and it just depends on which problem you're looking at, what's the best way. Sometimes the best way is to find the Cartesian equations for both and just try to solve simultaneously both equations. I think that works here pretty nice. So I think that's the that's the approach I'm going to take. I'm just going to convert these both to Cartesian equations and then see where they intersect as a starting point of my analysis. So how do you convert, like what's the Cartesian equation here? I think of it this way. Cosine squared pi t, right? Plus sine squared pi t is what? It's 1, right? And you can get a cosine pi t and a sine pi t from those expressions up there, right? Like 3 minus x divided by 5, quantity squared, plus what's the sine? Solve for sine, I've got y minus 1 over 5, quantity squared. So there, I've eliminated time for Carl's equations. So this is the Cartesian equation of Carl's trajectory. I can rewrite this as x minus 3 quantity squared plus y minus 1 quantity squared equals to 25, which is pretty nice. That's a circle, radius 5, centered at 3, 1, right? Graphically, I own that. Here, the way to eliminate the time is to just solve for t, right? Like t is equal to, it's equal to x minus 6 divided by 2, right? From the x equation. But from the y equation, solve for t, what do you get? I get 5 minus y over 4. Did you guys get that too? I think so. Okay, so then this is a line, right? So this gives me 2x minus 12 equals to 5 minus y, multiplying both sides by 4. which gives me that y is equal to, looks like 17 minus 2x. So now I can, basically I can think about this problem graphically now. So I've got 3, 1, right? My radius is what? 5, right? Oh, I'm not sure. I may have chosen a poor scale for my drawing. We'll find out soon. Roughly speaking, this is the path. This is Carl. And Carl is traveling, I'm not sure which way he's traveling. As time increases, what happens to sine when you're in like t equals 0 to pi over 2, what happens to sine? Sine increases, right? Or t equals 0, I should say t equals 0 to 1. Yeah, okay, so this is like t equals to 0 for Carl. This is like t equals 1 Carl time. T equals to 2 Carl time. Did I say 2? I'm wrong. What should I say? 0.5, right? This is t equals to 1. Down here is t equals to 1.5. I'm just thinking about plugging in times into the formula for Carl, and the fact that like time 0 gives me 3 comma, it gives me, oh, I'm an idiot. Where am I starting? Put t equals 0, what do you get in Carl's formula? Excuse me. 3 minus 5, right? So t equals 0 is over here, isn't it? This is actually t equals to 1. So in other words, Carl's going clockwise. But you notice that the sine and the cosine for the Carl parameterization, they're not in the usual way, are they? There's a minus cosine rather than plus cosine, right? So I think it's clockwise. Am I wrong? I don't think so. Okay, so there's the Carl curve. Then Bob's curve is where? This is, again, this point is 3 comma 1. And this y-intercept of this thing is where? Um, 17, right? She's up like here somewhere, right? And its slope is minus 2. So, I don't know. Like, I'm not sure. These points of intersection are questionable. For my unless I've made a mistake in the graph. Okay. How do you find if their points actually intersect? It's pretty simple. Do what? Just plug this equation into that equation and see what you get. But anyway, I think I'm gonna stop. I just wanted to show you enough to get you started on this. You do have the solution, right, worked out in the book, but I wanted to show you the idea of it. I think we've done enough for you to see that, so we'll stop here.